We used to think that plasma jets in space were held firmly in place by magnetic fields, that if the field was strong enough, it could guide the plasma, like rails guiding a train, into narrow, stable beams. This assumption appears in countless models of black holes, newborn stars, and even artificial fusion devices. But a 2024 experiment published in Physical Review Research has revealed something unexpected. For the first time, researchers were able to directly observe a magneto Rayleigh Taylor instability inside a plasma jet that was actively being confined by a magnetic field. Instead of staying smooth and stable, the jet began to ripple and deform, growing flute like instabilities at its surface. The field didn't prevent the instability. In a strange way, it enabled it. And that changes how we think about plasma, because what we often picture as a clean, focused beam may actually be something far more dynamic, a shape shifting structure guided by tension, but always on the edge of breaking apart. Today, we're going to walk through what the researchers did, what they saw, and why it matters, not just for lab physics, but for understanding the structure of the cosmos itself. Let's begin by taking a look at the astrophysical model. Here, plasma jets are known to emerge from a variety of energetic cosmic systems, including black holes, pulsars, and young stars. These jets can stretch for vast distances, often appearing as narrow, high velocity beams of plasma, cutting through interstellar space. Magnetic fields are thought to play a critical role in this process. They are believed to collimate the jets, that is, to guide and confine the plasma into long, narrow streams by exerting magnetic tension along particular field lines. Within this framework, magnetic fields are seen as stabilizing forces. They take the natural chaos of hot, ionized gas and impose structure on it, channeling the energy into controlled, directed outflow. In many theoretical models and simulations, the assumption is that once a plasma jet is magnetically aligned, it will remain relatively stable, like a cosmic fire hose, steady and self contained. However, this tidy picture has started to unravel. High resolution observations of real astrophysical jets reveal they often wobble, twist, or even fragment into smaller segments. These jets can break symmetry, change shape over time, and exhibit complex internal structure. To explain these deviations from the idealized model, researchers have proposed a range of plasma instabilities. Among them is the magneto-Rayleigh-Taylor or MRT instability, a magnetic analog of a well-known fluid effect. Although predicted in theory and seen in simulations, until recently, this instability had not been directly observed in a magnetically confined plasma jet. So let's talk now about what the researchers did. Here they created a controlled plasma jet in the lab, using a setup designed to mimic the magnetic conditions found in space. First, they fired a high energy laser pulse into a solid plastic target. This interaction rapidly heats and ionizes the surface, producing a plasma plume that expands outward. It's a common method in laboratory astrophysics, used to generate short lived, dense plasma flows with velocities of tens of kilometers per second. What makes this experiment different is what the plasma encounters next. As the jet expands, it moves into a region with a strong externally applied magnetic field generated by a pair of Helmholtz coils. This field is aligned parallel to the jet's direction, effectively setting up the conditions for magnetic collimation. You can see the full layout here. It shows the laser striking the target, the expanding plasma, the positioning of the coils, and the trajectory of the diagnostic proton beam used to probe the system. To observe the magnetic behavior inside the plasma, the team used a technique called proton radiography. They fired a separate beam of high energy protons generated from a second laser driven source right through the plasma. As these protons pass through magnetic fields, they are deflected in measurable ways. It's a bit like shining light through rippling water. The paths bend, revealing subtle changes in the invisible structure. Here you can see the results. Radiographs showing how the proton beam was deflected by the evolving magnetic field. These patterns form a kind of shadow map, encoding the shape and motion of the field in space and time. What makes this study especially important is the temporal resolution. The images were captured with nanosecond precision, fast enough to freeze the formation of structures that evolve in billionths of a second. This allowed the researchers to directly visualize the onset and growth of the Magneto-Raleigh-Taylor instability. Until now, this had only been predicted in theoretical work and large-scale 3D simulations. But this experiment captured it directly in real plasma jets under controlled magnetic confinement. That's a major leap forward. Now let's talk about what they saw. As the plasma jet entered the region with the applied magnetic field, something remarkable began to happen. The jet did not simply glide along the field lines as the conventional models would suggest. Instead, it began to push back, expanding against the magnetic pressure and carving out a distinct structure known as a diamagnetic cavity. You can think of it like this. Imagine squeezing jelly into a tight elastic net. The jelly pushes outward, distorting the shape of the net, but the tension holds it in place, at least for a while. That's what the plasma was doing. Its internal pressure pushed against the field, creating a bubble like void where the magnetic field was locally excluded. This process is visualized here. What you're seeing is the proton radiograph captured at 4 nanoseconds after the laser shot, showing a darkened ring structure which corresponds to the magnetic field lines bending around the expanding plasma. But the symmetry does not last. Very quickly, the outer edge of the cavity begins to deform, rippling into rhythmic finger like structures. This is the Magneto-Raleigh-Taylor instability, the plasma analog of a well-known fluid effect. In classical fluids, this instability occurs when a heavy fluid sits on top of a lighter one. Gravity pulls the heavier fluid downward, and the interface ripples and buckles. In this case, the magnetic field plays the role of gravity, and the plasma is the heavy fluid. It begins to destabilize, forming periodic structures along its boundary. These patterns are clearly visible here. The once smooth edge of the cavity is now distorted by wave-like features, indicating the MRT instability in action. The researchers measured the dominant wavelength of the structure to be about 1.2 millimeters, and their growth occurred within just 4 nanoseconds, an extraordinarily fast timescale that underscores how rapidly plasma can self-organize under stress. Here you can see the result of a 3D magnetohydrodynamic simulation that mirrors the experimental setup. The simulated plasma forms the same flute-like protrusions observed in the lab, validating both the model and the diagnostic technique. These structures are not just lab curiosities. They resemble the kind of forms we see in natural plasma systems: solar prominences with their twisted spires, auroral curtains rippling with electric tension, and fragmented cosmic jets breaking apart as they traverse light years of space. This was the first time we got to see such a fine scale instability grow and evolve in real time within a magnetically collimated plasma jet. And it tells us something profound. Even when it appears confined, plasma is not passive. It pushes back, reshapes its environment, and builds structure faster than most instruments can follow. Okay, let's talk now about why this matters. What makes this experiment so significant is not just that it visualized an instability, it's that it confirmed a key prediction about how plasma behaves under magnetic confinement, and that has implications far beyond the lab. First, the instability could help explain why astrophysical jets, even those tightly collimated by magnetic fields, sometimes fragment or veer off axis. We've seen jets from black holes and protostars that twist, pulse, or break into disconnected segments. These behaviors have often been attributed to unknown external forces, but this experiment shows that the cause might be internal. The plasma itself, even when guided by magnetic fields, can destabilize from within. The flute like protrusions seen in the lab may be small, but scaled up, they resemble the structure of a much larger system. We see echoes of this behavior in solar coronal loops, for example, where confined plasma bulges, twists, and occasionally erupt. We also see it in supernova ejecta, where plasma plumes curl into filaments and knots as they race outward. What you're seeing here is a simulated 3D rendering of an instability closely matching the experimental results. And this shows how the features evolve over time in both experiment and simulation, validating the underlying physics. But the implications go deeper. This study strengthens our understanding of how magnetic confinement actually works or fails in plasma systems. It supports the idea that even in idealized setups, instabilities like MRT are not just edge cases, they're natural modes of behavior emerging from the very forces that are supposed to contain them. This work represents a scientific milestone. For the first time, a predicted plasma instability modeled in complex 3D magnetohydrodynamic codes was directly observed in a lab setting under well controlled conditions. It's a bridge between simulation and experiment, between theory and reality. Magnetic fields don't just tame plasma, they shape it. But as this experiment showed, even that shaping has limits. Inside a structure that should have been stable, the plasma found room to move, growing ripples, forming structure, and breaking symmetry in real time. Not through chaos, but through patterned instability. These dynamics are not just theoretical. They may underlie some of the most striking features we see in the universe, from solar arcs to galactic jets. And they remind us that plasma is not passive, it's an active, organizing force responding to tension with movement. There's still more to uncover about how plasma behaves when pushed, confined, or left to its own devices. But experiments like this bring us one step closer to understanding the dynamics at the heart of cosmic structure. We'll be watching closely as more of these hidden gems come into focus. Thank you so much for joining me today. I will link the publication in the description below. And don't forget to comment. Let me know what you think about everything. And until next time, take care.